Balancing equations. Remember, you're trying to get the same number of atoms on each side of the equation. The most difficult ones to be balancing will be oxygen and hydrogen. Lecture notes did cover a polyatomic trick, and combustion reactions. Let's take a look at this one for balancing. I have one arsenic on this side and one on that side, so they're already balanced. I have 3 iodine over here and 2 over here. They share a common number of 6. So if I put a 2 in front of this compound, I would have 6 iodines. I'd put a 3 in front of this one, I would have 6 iodines over here. Let's see if I did balance it all. I have 2 times 1 arsenic, but I only have 1 over here. I need to put a 2 in front of here. This equation is balanced. Let's take a look at this one. I have 1 potassium on this side, 1 on this side. 1 chlorine over here, 1 chlorine over there. My oxygens aren't balanced. I have 3 here and 2 over there. Again, they share the common number of 6. So I've put a 3 on this side and I put a 2 over here. I will have 6 oxygens on both sides. However, I now have 2 potassiums and 2 chlorines. I only have 1 of each of those over here. By putting a 2 in front of this, I will now have the equation balanced. On this one, I'm going to start with aluminum. I have 2 aluminums over here. I have 1 here. If I put a 2 in front of this, my aluminums are now balanced. Again, I have 3 oxygens over here and only 2 over here. They're not balanced, but they do share the common number of 6 again. So if I put a 3 here and a 2 over here, I will have a balanced equation for oxygen. I'll have 6 on each side. Let's check my aluminums though. I have 2 times 2 is 4 aluminums, and I only have 2 over here. I would have to erase that and put a number 4 down. Happens quite often when you're doing balancing and when you're rechecking that you would have to change numbers, so make sure you use pencil. Let's take a look at this. One of the things I do notice right away is that I have carbonate. However, I still have 1 carbonate on each side. Let's look at our metals. I have 1 strontium here, 1 strontium there. I have 2 potassiums here, but 1 over here. I'm going to put a 2 in front of here so that my potassiums balance. I have 2 chlorines over here, and now, because I put a 2 over here, I have 2 chlorines. And if you look at this, it is balanced. I do want to make a note at this point that on the exam, sometimes the question can be, what is the sum of the coefficients of the balanced equation? What is the sum of the coefficients of the balanced equation? Remember, even though these are not written here, there is a 1 in front of these compounds. And when you do add up the coefficients, you will get an answer of 5. That would be the sum of the coefficients. However, sometimes on the exam, they will want to know a specific compound and ask you what is the coefficient in front of that compound when the equation is balanced. Let's take a look at this one. There's a lot of carbons and hydrogens and oxygens in here, and it looks a little scary, but it is a combustion reaction. Remember, combustion is a carbon-hydrogen that burns in oxygen and it always has the same products. However, this one was flipped. It had the oxygen first and then the carbon-hydrogen. But you use the same rules when you balance. Start with carbon. I have 1 carbon on this side, 1 on that side. I have 4 hydrogens over here and only 2 on this side. Putting a 2 in front of this will give me my hydrogens to be balanced. Let's sum the number of oxygens on the right side of here. I have 2 oxygens over here, and I have 2 oxygens from this compound. So my total number of oxygens on the right side is 4. Remember, 2 times 1. I need to put a 2 in front of here to have the same number of oxygens. That is a balanced equation. Lewis structures should always start by counting the valence electrons. Make sure you draw the central atom and then use 2 electrons to bond to the central atom and distribute the remaining electrons so that all of them will have 8 except for hydrogen, as it only needs 2. we're going to draw the Lewis structure for ammonia. Let's do the valence electron count. There's 5 from nitrogen and 3 from hydrogen with a total of 8. My central atom is nitrogen. I'm going to surround this with my 3 hydrogens, and then I'm going to bond them to the central atom. I'm going to draw these bonding electrons as a straight line. The straight line represents 2 electrons each. So that'd be 2, 4, 6 electrons that I used for bonding. That leaves me with a total of 2 electrons left to make sure that everybody has 8 except for hydrogen. Nitrogen only has the use of 6 electrons, but I have 2 electrons left. I'm going to draw my 2 electrons paired next to nitrogen, and when I keep track of it all, I have used up all my electrons. Nitrogen has 8 and hydrogen has 2, so they are happy. Let's look at this. Which one has the greatest number of lone pairs of electrons? There's 8 electrons on methane. The central atom is carbon, and I'm going to surround it with the 4 hydrogens. As I draw the bonding electrons to carbon, each of those are worth 2 electrons, and I have used up 8. After I use up the 8, I have 0 electrons left. All of the electrons in methane are involved in bonding, so the answer to this one is there are no lone pairs of electrons. They all are involved in bonding. Hydrogen has 2 electrons for valence electrons. Here is hydrogen. I am going to bond my hydrogens together. That's 2 electrons for bonding. I have 0 left. Again, all of the electrons for this one were involved in bonding, so there is no bonding electrons, no lone pairs of electrons. Water. Central atom is oxygen surrounded by 2 hydrogens. Let me bond those hydrogens to oxygen. It requires the use of 4 electrons. When I minus it, I have 4 electrons left. I notice hydrogen is happy because they have the use of 2 electrons, but oxygen needs to have 8. I'm going to take the last 4 electrons and surround oxygen, and that leaves me with no electrons left. Now the number of lone pairs of electrons on this one is 2. I have 1, 2 pairs of electrons that are not involved in bonding. Let's see if there's another one that has a greater number of those. Hydrofluoric acid has 8 valence electrons. Here's the central atom. Let me bond that to the hydrogen. I've used up 2 electrons, and I have 6 left. I'm going to surround fluorine with these 6 electrons. Remember to pair them up. That's how electrons are in electron configurations. They pair up. I've used up all 6 electrons, so I have none left. Now the number of lone pairs of electrons in this one is 3. Surrounding fluorine. Remember, water only had 2. This one has 3. I wonder if it's going to be the one that has the most lone pairs of electrons. Fluoride gas has 14 electrons. Let's bond our electrons here. Or bond our atoms. I'm going to use 2 electrons. I have 12 left. Again, they each need to have 8 electrons. So as I'm doing this, I've used up 6 electrons. 7, 8, 9, 10, 11, 12. I've used them all up. Let me make sure all of them have 8 electrons, and they do. This one has 1, 2, 3, 4, 5, 6 pairs of electrons that are not involved in bonding. So here's ethanol. It burns in oxygen, and it says it forms carbon dioxide and water vapor. That is exactly a combustion reaction, a carbon-hydrogen compound burning in oxygen making the same products. You can have an alcohol, which is ethanol, or you could have maybe a carbohydrate. But no matter what, these will burn in oxygen and always make the same products. Carbon dioxide, 16 valence electrons. Here's your central atom. We're going to use 4 electrons for bonding, and that leaves us with 12 left over. You can't use any more than that. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now oxygen has 8, but carbon only has 4. This is when you start thinking about drawing double bonds. I'm going to take one of these double bonds to the oxygen, and I'm going to bring it down, and I'm going to see if that solves the problem for carbon. This has 2, 4, 6, 8. Oxygen still has 8. This still has 8, but carbon only has 6. That means I need to take more electrons and make them into a double bond. It just so happens carbon dioxide is a 2 double bonded compound. Notice I'm still using the same number of electrons that I was given. I just needed to take the single bonds and make them into double bonds.